Friday, we introduced position time graphs. In fact, we introduced graphing in general for the first time. We said a couple things before we looked at these specific graphs that you see up on the board right now. For instance, the title of the graph, in this case, position time graph. The title of the graph is always in the same form. Which axis always comes first, x-axis or y-axis? Doesn't matter what the graph is. Position time graph, velocity time graph, force versus time graph, force versus displacement graph, doesn't matter. Which axis from the graph always comes first? The y-axis, good. So in this case, you can see on all these graphs, the y-axis is position, y-axis comes first, and then it's going to be, after that, the x-axis. Call it position time, position versus time, position as a function of time, but it's always y-x. Y comes first. We also talked about variables, the manipulated variable and the responding variable. The x-axis of your graph, the second name in the title of the graph, will always be which variable? The manipulated or the responding variable, the one that you change or the one that changes because of that? Louis? The manipulated variable, good. What about the control variables? You guys learned about that, right? Obviously, the y-axis is going to be responding. Where do the control variables appear on this graph? What's a control variable? I'm sorry? No. What is a control variable? It's the variables that don't, they remain constant. They don't change. If they don't change, why would we put them on a graph? It doesn't show us a relationship when they're not changing, right? So the control variables aren't going to go anywhere in the title. They're not going to go anywhere on the graph itself. Only the manipulated and responding variables. Yep. I'm sorry? No. Without knowing the exact experiment, we don't know what the control variables are. We just know that they're the ones that stay the same. Everything else stays the same. If we're talking about a car driving down the road, the control variable would be the type of car, for instance, the conditions of the road, and so on. Okay? Those remain the same. Therefore, we're not going to plot those on the graph itself. Just the manipulated, just the responding variable. Okay. So time would be the manipulated here. Position would be the responding variable here. Position would go first in the title. Time would go second in the title. What does that first graph mean? That first straight line position time graph mean? Constant something, right? Because it's a straight line. Constant what? Yep. Good. It's moving at a constant rate. In other words, we can simplify that a little bit. It's a constant. Sorry? Yeah, well, let's say constant velocity. Yeah, but speed's close. Okay, constant velocity. What about the second one? Straight line, still constant something, but constant what? Tony? It stopped. So you can say it's a constant velocity of 0, or it's probably easier just to say it stopped, right? But technically, it's a straight line on a position time graph. It is a constant velocity. It just doesn't have any value. What about this one? Right? Constant. Okay, yeah, it's a negative slope. Straight line means velocity, constant velocity, right? So it would be a constant negative. No, constant negative. Time's changing, right? Constant negative velocity, right? Anytime on a position time graph, you have a straight line, it's a constant velocity. But as Ryan correctly said, this is a negative slope, so it would be a constant negative velocity. What about this one? Now they get a little bit tricky, right? Not quite as tricky now though, because we've gone over these on Friday. Yep. This is acceleration, speeding up. The object is increasing in velocity. And what about this one? Deceleration, slowing down. The object is decreasing in velocity. Good? I showed you a couple on Friday that didn't really work, right? Why didn't they work? Remember I showed you this one? And I showed you this one? Why didn't those ones work? Jordan? Right. You have to move forward in time, right? You have to move forward in time. This one's going back in time. This one's just staying in constant time, which can't happen, right? You can't go somewhere and not have any time elapsed. So you won't see those on a test. I just wanted to go through those so that you'd understand graphs a little bit better. Same? Yeah. Good? All right, on Friday, we also went through this process here. We had a position time graph. And I think on Friday, I put up a straight line on that position time graph, didn't I? How do we find the position on a position time graph? Somebody gave me a good answer right away. I don't remember who it was. Jordan? Go up and over. Good. That's it. Up and over. If I want to find the position right now, at that moment in time, go up and over. If I want to find it right now, go up and over. All we're going to do to find the position on a position time graph is go up and over. If you ever want to find whatever's on the y-axis of any graph, just go up and over. The displacement on a position time graph. Who can give me real quickly the definition of displacement? Yep. Good. The change in position. So how are we going to find the displacement on a position time graph? Good. Go up and over twice, then subtract. In other words, get the final position, get the initial position, and then subtract the two. That's going to give us displacement. Now, the average velocity, there were two ways that we could think about this one, although in the end, they both worked out to be the same thing. Average velocity. Alana, what's one of the ways that we could find that? Good. Slope is rise over run. Now, sometimes you learn slope in math class. I'm not sure how you guys learned it, but sometimes you learn it in math class as delta y over delta x instead of rise over run. Do you guys remember that? Delta y over delta x? When you guys think of slope, what do you think of? Rise over run or delta y over delta x? Rise over run? Okay, that's what we'll stick with then. Okay, that works just fine. Okay, how much it goes up divided by how much it goes over. Rise over run. What's the other way? What's the equation we learned on day 2, I guess it was, at Physics 20, that describes velocity? I'll give you a hint. It's the only one we've done. Stephanie? Good. Total displacement divided by the total time. We know how to find the displacement. Up and over, subtract the two. The time is just look off the x-axis. In the end, this is the same thing as this. Because the rise is the change in displacement. The run is the change in time. Now, this is where we left off with on Friday. The instantaneous velocity. Instantaneous means the velocity not over the entire trip, but the velocity at one moment in time. At one single moment in time. So in other words, I could ask you for the velocity right here, or here, or here, or here, or here, or here, or anywhere along that path. Because it's a constant velocity, and we know that because it's a straight line, because it's a constant velocity, if we've already found the average value right here, then the velocity anywhere along that line is the same as the average value. So if I did the math for the average velocity and got 10 meters per second, the average velocity over this entire trip, what would be the velocity right here? 10. What would it be right here? 10. Here? Here? It's 10 everywhere, right? It's not changing. It's got to be the same everywhere along there. Does that make sense? Now, if you got a curved line or something that looks like this, okay, changes a little bit. We'll deal with that a little bit later, okay? But right now, we'll just go with that nice straight line. If you've got a constant velocity, then the instantaneous velocity anywhere along that path will be the same as the average value. All right. All right, take a look at the worksheet that you just got handed out to you, the front side for the example problem. Same one that appears up on the board here right now. It says, got a position time graph. Okay, we know that because of the title, we know that position would go on the y-axis, although it's already done for me. We know that which variable would be the manipulated variable here, position or time? Time, because it's on the x-axis. Seems odd for time to be a manipulated variable, a variable that we change, but that's what it is, okay? When we do an activity tomorrow with this, I'll explain to you a little bit better why time would be the manipulated variable. We've got 5 questions to answer here. What's the position of the object in the graph to the left at t equals 10 seconds? How do we do that? A little bit trickier here because this time, although we do have a constant velocity, it's sloping downwards, which means it's a constant negative velocity. What's the position on this graph at 10 seconds? How do we get that? Bart? Up and over. So let's go up at 10 seconds. Let's go over. The answer would be 30 meters. 30 meters to the east. We'll just make east positive so we don't have to write that in every time. You want to find out a value that appears on the y-axis. Just go up and over. What's the displacement between 0 and 10 seconds? Oh, good question. The displacement between 0 and 10 seconds. Up and over, subtract the 2. In other words, final position minus initial position. Final position is 30 meters. The initial position is what? Initial position is what, Jared? Yeah, 80, good. 30 minus 80 is what? Looks like neg 50. What's the negative mean? West. Look at this, guys. You were 80 meters to the east. Now you're 30 meters to the east. In order to get to 30 meters to the east, which way did you have to travel? To the west. 50 meters to the west in order to get there. Okay, I don't see west anywhere on this graph, but remember, displacement is not what you read off of the graph. It's the change in what we read off of the graph. The average velocity between 0 and 10 seconds. Who would rather find this by calculating the slope? Okay, who would rather find this by using v is equal to delta d over delta t? Okay, it's about 50-50. Okay, this time we'll go with delta d over delta t. But if you want to go with slope, you go ahead. Same thing, really. The displacement is negative 50 meters. Time is 10 seconds. The average velocity is negative 5. What does the negative mean this time? To the west. Listen, if I was traveling to the west, my displacement was neg 50 meters to the west, then of course my velocity is going to be to the west. It's got to be a negative. Instantaneous velocity now. Instantaneous velocity. The velocity at 1 instant in time. What is the velocity at 2 seconds? What do you notice about this line? What do you notice about the velocity over this entire trip? It's constant. It isn't changing. So it's negative 5.0, right? If it's negative 5.0 on average over the entire trip, but it's not changing, then it's got to be negative 5 here and here. All right, what I'd like you to do right now is flip over the page. You're going to see 4 questions. I'd like you to do those 4 questions now. Okay, I'll be walking around. Call me over, stop me if you're struggling with anything, okay? All right, everyone, we're going to take a look at question number 1 on the worksheet. Okay, we got a position time graph. It means time is our manipulated variable, positions are a responding variable. If we titled this, which we really should every time we have a graph, it would be position versus time or position as a function of time. We want to find the position at 7 seconds. What do you do to find the position on a position time graph? Yep, up and over. So what is the position at 7 seconds? Let's go up. Let's go over. What does that work out to be? What's that work out to be? 30 meters. Good. Good. The displacement between 0 and 5 seconds. Displacement. Displacement is change in position. The position at 5 seconds is, sorry, that's 4. Having a little trouble with my numbers. Position at 5 seconds is 30 meters. The position at 0 seconds is 0. What's the change in position there? 30 meters. Same answer. The average velocity now between 0 and 5 seconds. Now we got to do a calculation. It's more than just subtraction. Who wants to do, who likes slope? Who likes v equals d over t? Let's do it slope this time because we did it v equals delta d over delta t last time. The slope is the rise over the run. What's the rise between 0 and 5 seconds? How much does it rise here between 0 and 5 seconds? Derek? 30 meters. How much does it run there? How much to the right does it go, Derek? 5 seconds. 30 divided by 5 is going to give me 6.0 meters per second. The average velocity between 0 and 9. This is a bit trickier. Hey, we haven't done one exactly like this, although we do it the same way as we've done the question that we did as the example. The average velocity between 0 and 9 seconds. Let's do the equation for this one. In fact, for this one, we have to do the equation because it's not a straight line, right? It goes like this, and then it goes like this. You can't do slope when you got something that's not a straight line. So we have to do v equals delta d over delta t for this one. The displacement between 0 and 9 seconds is 30 meters. Same as it was in the last question. The time between 0 and 9 seconds is 9. 30 divided by 9 would be 3.33, I think. 3.33 meters per second. Stephanie asked earlier on that great question about direction here. We're not specifying north, south, east, west, right? 3.33 in the positive direction, whatever that is. Okay, positive direction. The instantaneous velocity at 3 seconds. The velocity at this moment in time. What is it, Bart? Good, good. I thought that some of you might say 3.33. You can't use 3.33 because it's on average 3.33 between the start and the finish. That's not constant. Okay, but over this interval from the start to 0 to 5 seconds, over that interval, it is 6 meters per second everywhere. So we're going to say it's 6 meters per second there. What about at 8 seconds? F. 0. There's no calculation to do there, right? Okay, it's a straight, flat, horizontal line, which means it's stopped, which means the velocity must be 0. If you want to use an equation, go ahead. What's the displacement? 0. Time is, doesn't matter. 0 divided by the time is going to be 0. Okay? Okay, keep working, guys. We'll give you another few minutes, and then we'll take a look at another question, okay? Take a look at the question number 4 on that worksheet now. Again, position versus time. Position's on the y-axis, so it comes first in the title. Okay, time is on the x-axis, so it's our manipulated variable. Position is our responding variable. We're going to find the position at 6 seconds. Okay, let's go up and over. The position at 6 seconds is 3.0 meters. At 0 seconds, well, there's nothing to go up and over there. It's just 0 meters. At 8 seconds, up and over, the position is about 5 meters there. How many people have those 3 answers correct? Good. Excellent. The displacement between 0 and 8 seconds. Remember, displacement is defined as the change in position. We have the position at 0. We have the position at 8. Let's subtract the 2. 5 minus 0 is 5 meters. So the displacement between 0 and 8 seconds is still 5 meters. Now, the average velocity between 0 and 8 seconds. We said a few minutes ago that you can't do the slope when you don't have a straight line, when you don't have a constant velocity. So we don't really have much of a choice here. We've got to do the velocity equation, v equals delta d over delta t. Now, I don't care with this equation whether it's a straight line or not. Okay, it's average velocity. The displacement there between 0 and 8 seconds is 5 meters. The time is 8.0 seconds. 5 divided by 8 would be, I believe, 0.625. Is that right? 0.625 meters per second. Now, at this point, tell me right here, at 0.5 seconds, is it slower than 0.625 or is it faster than 0.625 there? It's slower. I don't see a number for velocity there, but I know that since it's increasing in speed at the beginning, it must be slower than that, right? What about at the end? Slower or faster than 0.625? Faster. It's speeding up from 0 to something faster, 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 faster. Okay? Somewhere in the middle here, we're going to be at about 0.625 meters per second. We don't know exactly where. Somewhere in the middle, it's going to be 0.625. But on average, over the entire trip, it's 0.625. All right? Is that okay? Okay. That's it for today, guys. If you finished the worksheet, that's great. You have no homework. If you're not finished the worksheet, then let's get it finished, and we'll take a look at the answers to question 2 and 3 tomorrow, okay, if you need to. All right?